Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course, uh, being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And so this was a 12-week course. So we have discussed all the uh, 12 weeks one by one, week by week. So now this is the last session of this course, and we just want to briefly get through this whole course, okay, in a single session so that we can have a overview of the whole course. Uh, so we shall be doing this only in this particular session. Instructor for the course is has been Professor Niranjan Sahu, right? And I have been the teaching assistant for this course. So let's wait for a few minutes to see if somebody joins. After that, we can just continue with the session. Thank you. Okay, so we can start with the session. So we shall briefly discuss the topics. So it was a 12-week course. So we started with introduction, then we moved on to wave propagation in compressible medium. Then we discussed quasi one-dimensional isentropic flow. So in week 2, we discussed 1D compressible flow. Then we learned normal shock modeling. Okay. Then we saw expansion waves and oblique shocks. We learned about oblique shocks, expansion waves. So this we did. Then supersonic nozzles and diffusers we discussed. And then how heat transfer and friction affect our compressible flow in week 10. At last, we saw majorly experimental facilities for study of compressible flows. Okay. So one by one. So in week 1, properties of fluids. Yes. So in introduction, properties of fluids like what is intensive property, what is extensive property, right? Extensive means by virtue of its extent, right? Like mass. And intensive means the extent does not matter, like, right? For example, density, right? Then classification of fluids, sorry, classification of fluids was done. So different classes like inviscid and viscous flow, right? Where viscosity comes into picture. This is viscous flow, and inviscid where we say that viscosity is absent, right? Then internal and external flow. Internal flow is example is pipe flow. External flow is flow over a plate, a flat plate, that is external flow. Then incompressible and compressible flow. So for your air, if your Mach is greater than 0.3, your flow starts to become compressible, right? Steady and unsteady flow, right? With time, if your flow is at some location, if the flow is not changing with time, so that means it's steady. And if it is changing, then it means it is unsteady. Its velocity is changing, its pressure is changing, right? At that location. Then laminar and turbulent flow is there. A natural and forced flow. Yes, yes. So example of forced flow is flow in your fan or compressor. A natural flow example is boiling of water, right? So this is there. Then fluid as a continuum. So for the study of fluids, we consider fluid to be as continuum, right? Continuum means the fluid is continuous and there are no gaps in between in the fluid, right? That is what we suppose for our fluid study of fluid dynamics, right? And in fluid dynamics, because we are studying compressible flows, so that is the reason why this has been introduced here. So for that, we have so which flow we can call as fluid we can call as continuum. So for that, we have Knudsen number, right? What is Knudsen number? Knudsen number basically is ratio of your molecular mean free path to your characteristic linear dimension of flow field. Okay, so this is your Knudsen number. So for fluid to be continuum, this has to be less than 0.01. So this is there. Then, so this was introduction of basic concepts. Right? Then we moved on to week number 2, where we studied about wave propagation in compressible medium. Okay. So week number 2. Yes. So wave propagation in compressible flow. So we learned this through example of a piston. So we were taking a piston this way, okay, in a tube, and we were moving this piston in this direction, and this was going to give us a compression wave. So if we keep on moving this, it is going to give a series of compression waves, right? And then in compressible flow properties, so we learned about acoustic speed, right? And about Mach number. Acoustic speed, basically speed of sound. And it can be given by these formulae. Okay. And Mach is your velocity by acoustic uh, speed. So this is what has been discussed in compressible flow properties. Yes. Then important is your isentropic relations. Important topic. So in isentropic relations, first is your T naught by T. This is your stagnation. This is your stagnation. This is your static. Okay. And this is related to your specific heat ratio and your Mach in this manner. Right? 1 plus gamma minus 1 by 2 m square. Right? So this means that if we have initially some stagnation temperature, this T naught, and we are expanding this gas, okay, such that we get some static temperature T, okay, and we have in this case flow of the Mach of the flow is m, so we can relate stagnation temperature, static temperature, and Mach this way, right? And can we comment on pressure from here? Yes. So pressure is related to your temperature this way. So all these are stagnation isentropic relations. Right? And your rho by this is T naught by T 1 by gamma minus 1. So this is there. Then governing equations are there. So so 1D equations. First is your continuity equation. So this is written this way. Then your momentum equation, which is given this way. Then is your energy equation, which is given this way. So this is there in your week number 2. So where we got introduced to your compressible flows. Okay. Then comes your week number 3. So in week number 3, area velocity Mach number relation has been discussed. Okay. So I'm taking the topics such that I'm briefly able to discuss every week's content. So this is your week 3 area velocity Mach number relation. So this is given as this. Okay. Now if you see the heading of this week, it is quasi one-dimensional isentropic flow. So quasi means, so 1D is this, flow is moving in this direction. Quasi means your area is also changing. Your flow is moving, so it can be this way. It can be this way. Okay. Flow is moving in this direction. So this is 1D, this is quasi 1D. Okay. Now, if we see this area velocity Mach number relation, so it is in relation to this quasi 1D flow only. Now you see first case. So in first case, because it's a convergent duct, okay. So area is decreasing from here to here, right? So your dA is going to be negative, okay. Now, case 1, if your Mach is greater than 1, in that case, because your left hand side is negative, so your right hand side has to be also negative. Because m square minus 1 in case A is going to be positive, then your du is going to be negative. Okay, so it means for supersonic flow, in a convergent duct, your velocity is going to decrease. And if your Mach is less than 1, it means your left hand side is negative. Your m square minus 1 is also negative. Your du will have to be positive. Then only both the sides are going to be same. So which means your velocity is going to increase in a convergent duct. Right? So here your area is increasing. So your dA is going to be positive. Now, if Mach is greater than 1, in that case, because m square minus 1 is going to be positive, so your du is also going to be positive. If Mach is less than 1, because your left hand side is positive, so right hand side has to be positive. So minus multiplied by minus is going to be positive. So your du is going to be negative, right? So for your subsonic flow, when duct is divergent, your velocity is going to decrease, right? So this is about du, this is about du, this is about du. Okay, so this is there. I hope there are no doubts in it. If there are, you can just give your doubts in the comment box and I'll be happy to answer. So here we started with normal shock. So how the shock waves form in one-dimensional medium. This is there. Then flow properties across normal shock. This is there. Then entropy change across normal shock. This is there. So how do we model a shock wave in 1D medium? So we take a piston, we move it in this direction. Okay. So this moving of piston is going to give you a compression wave. So this is going to give you a compression wave this way. And this is going to give pressure rise. Okay, so this corresponds to this. So this is pressure, this is x-axis. Now again, this is first movement. For your second movement, you are going to have, so I'll not show the movement, I'll just show the waves. This is first, this is second. Like this. So this is there. So one important thing is that, let's say this is your first wave. Okay. This is your first, this is your second wave. First, this is your second, this is your third wave. So the speed of your second wave is going to be higher than the speed of your first wave. Speed of your third wave is going to be higher than speed of your second and first wave. Why so? Because as the compression wave moves, right? So this region, its static properties are going to change, right? Its pressure, static temperature is going to change, and that change contributes to increase in the velocity of the next compression wave that comes. Same is with the third compression wave and so on. And eventually what happens that these compression waves coalesce at some point, right? And give rise to one single wave that is your shock wave. Okay, so this is how we can model a shock wave. And flow properties across shock wave. If this is your shock, Flow is moving like this. This is upstream of shock. This is shock. This is downstream of shock. So now the change in the Mach number across the shock, right? First is that your across the shock, your Mach is going to decrease drastically across the normal shock. So we are talking about normal shock, okay? Later we have seen oblique shocks also because we have discussed oblique shocks, so I can just mention oblique shocks. So across your shock, your Mach decreases, and the decreased Mach number can be found out using the upstream Mach number M1 and your gamma, specific heat ratio. Okay, so this is there. Static density also can be found out, which is gamma plus 1 M1 square by 2 gamma minus 1 M1 square. So this is static density ratios. Now your static properties increase across your normal shock. So your rho 2 is going to be higher than your rho 1. Same way pressure, static pressure 2 is going to be higher than static pressure 1. So this is there. And for entropy change across the normal shock, this is the formula. Or if we have total pressures, so this can also be used. Now talk about your normal shocks also. Your total pressure decreases, okay, across your normal shock. So there is loss in pressure. But if you talk about total temperature, that remains same. Okay. So this is about week 4. Now in week number 5, 2 topics are there. That I'm going to discuss. So first is your limiting Mach number. So this is in relation to your normal shock only. So we have seen that with this normal shock, so your Mach decreases. Downstream of your normal shock, your Mach is going to decrease, right? But there is limit to this decrease. Okay. So below a certain level, your Mach is not going to go down below a certain limit. Okay. So for this, we have limit of this. Okay. For your gamma is equal to 1.5, which corresponds to air, your limiting Mach number is 0.378. Same way, there are limiting static properties. Okay. So limiting static density ratio is there, which is this is M1. Okay. So this is there. Then Hugonoid relation is there. So first is this. About first relation is this. Second is your pressure ratio. which is so this is there. So 2 and 1 here corresponds to this only. This 1 and 2. Okay, 1 is upstream condition of your normal shock, and 2 is your downstream condition. So P is for pressure, gamma is for specific heat ratio, and this is for your specific volume. Okay, that is 1 by rho. So this is there. And then there is comparison between your isentropic compression and your Hugonoid curve, which gives your shock wave compression because of shock wave. So this is somewhat like this. So this is for your Hugonoid relation from Hugonoid relation. This is from isentropic. This talks about compression, okay? Because across your normal shock, you see your pressure increases. Your P2 is greater than P1, right? So basically what is happening across your normal shock? Your flow is getting compressed. Yes. So now if the compression is isentropic, which is not the case of normal shock, okay? So this is between P and this specific volume and pressure. Then so for your decrease in specific volume, so for same decrease in specific volume, if you see this, okay, this case, if you see, the decrease in specific volume is same at point A, let's say. Okay. But then pressure increase in your Hugonoid curve is greater than pressure increase in your isentropic curve. But what happens is that in your shock compression, because there is loss in total pressure, and then there is increase in entropy, so the efficiency of compression is less in your compression, and it's high in your isentropic compression. So this basically is the difference between these two types of compressions. Okay. Then next is your formation of expansion waves, Prandtl-Meyer expansion waves, oblique shock waves. Okay. So how we can model expansion waves? Again, a piston we are going to take, and we are going to move piston in this direction. Okay. So as we keep on moving, it is going to give a series of waves, pressure waves, which we call as expansion waves. Okay. Now, what happens is, so let's say we have one expansion wave, then we have second expansion wave. Now the speed of second expansion wave is going to be less than the speed of first expansion wave ISO, because if we compare it with normal shock, the property change here is opposite. So your pressure is going to decrease. Okay, your temperature, static pressure and static temperature both are going to decrease here. Okay. So that is the reason your speed of second expansion wave is going to be lower when you compare it with first expansion wave. Then Prandtl-Meyer expansion waves. Prandtl-Meyer expansion waves are there. So what are Prandtl-Meyer expansion waves? So this basically is the scenario. Your flow is moving in this direction, and then it is diverted away from itself. If it is diverted towards itself, then we get a oblique shock. If it is being diverted away from itself, then we are getting an expansion fan, right? So this is going to be a expansion fan with series of expansion waves. Okay. So this will be the start of the expansion fan. This will be the end of the expansion fan. And the start and end, the angle between these two expansion waves is phi, which we call as fan angle. Okay. Now forward Mach number is this, which is mu m1. Rearward Mach number is this, which is mu m2. This is theta is deflection angle. Okay. Yes. Now mu m1 is sine inverse of 1 by m1. Mu m2 is sine inverse of 1 by m2. Then there is Prandtl-Meyer function. Okay. Which is this. This. So we can find out the deflection angle based on Prandtl-Meyer function, that is nu, and fan angle we can also find out, which is this is geometry, basic geometry, we can figure it out. Okay, how the fan angle and different angles have been correlated. So this is there. Then oblique shocks. So first, what is an oblique shock? So we are having this flow and we are diverting this flow. This is what basically. We are diverting this flow towards itself. Okay. So this first of all is going to give a shock, which is not normal. Okay. And this diversion has given you an oblique shock. Now there will be properties change across your oblique shock, right? This is your deflection angle. This is your beta. Okay. Beta we call as, I believe, shock angle. So your Mach will decrease, but the decrease will not be as drastic as it was in your normal shocks. Okay. Then your static properties are going to increase, but your stagnation temperature does not change and your stagnation pressure decreases. Okay. Also, your entropy is going to increase, so this remains same as was in your normal shock waves. Like we talked about normal shocks, right? If you see, we talked about normal shocks and the properties change across normal shock, right? Now, what happens in oblique shocks is that, so let's say we have this flow, right? So this flow is going to have one normal component and one component parallel to your oblique shock. Okay. This is your normal component, this is your parallel component, this is your resultant component. So if we consider just normal component and the oblique shock, so normal components act, and if we see normal component and oblique shock, so this oblique shock is acting as a normal shock for your normal component, right? And for your parallel component, this oblique shock is not going to have any effect, right? So when we talk about MAC change across the oblique shock, so we deal with this normal component only, and then we get to the resultant MAC. Okay, so that is there. And then there are oblique shock relations, right? So that we can see from the lectures only, but this point is to be noted that only the normal component is to be taken into consideration. Then if you talk about theta beta M relation, so this is the relation. Okay, so theta is deflection, beta is your shock angle, and your M1 is your upstream Mach number. So this is how these three can be correlated. So about oblique shocks, expansion waves, week number 6. Then week number 7 we'll take after taking a short break. So let's take a short 5 minutes break. After that, we will continue with session. In week number 7, we see wedges, cones, and shock expansion theory. So wedges and cones are based on your oblique shocks, okay? And shock expansion theory takes care of or takes help of both oblique shocks and expansion waves. There's one difference between these two, week number 7. So when we are having a supersonic flow over these two, so how these two behave. So this is for your wedge and this is for your cone. Now if you take one Mach, so you'll see for same Mach, your theta max is greater for your cone and theta max for your wedge is less. Okay, which is because of 3D relieving effect. Okay. So if your deflection is beyond theta max, your flow is going to get detached. Okay. So theta beta M curve is important here. Okay. Which looks like this. So this is beta, this is theta. This is 90 degrees, this is 0 degrees. Just like this. So this for some Mach. So this is for some Mach M. Okay. So if you move in this direction, so this will go like this. But for this Mach M1, so this is M1. Okay. So this is your theta max. Beyond this, if you increase the deflection angle, theta, this theta angle. Beyond this theta max, if you are going to increase your deflection angle, you are going to get a detached shock. Okay. So here you are going to get inside, let's say we have theta 1. So you are going to get two solutions here for one theta. One corresponds to your weak oblique shock and one corresponds to your strong oblique shock. So two solutions you get. Your shock expansion theory is used in your diamond airfoil. Okay, so this is Mach M1 greater than 1. Here you are going to have oblique shocks because flow is turning towards itself. Here you are going to have expansion fan because flow is moving away. Here again you are going to have this is trailing edge oblique shock. So this is leading edge. Is there. Now here you can find out the drag per unit span. So this is region 1, this is region 2, this is region 3. So drag per unit span can be given by pressure in region 2 minus pressure in region 3 into T. T is the thickness of this airfoil. Okay, diamond shaped airfoil. Okay. Shock polar pressure deflection diagram, regular reflections of oblique shocks, and wave reflection from free boundary. So week 8. Shock polar. So shock polar basically discusses about your velocity components. Okay. X and Y components. So across the shock, if this is V2, then X and Y components are like this. Now for different theta values, if we draw this diagram, okay, so this is going to be this way for different theta values. So it will be something like this for different theta values, right? So let's say we have some theta value. So to this line cuts the shock polar at 2 points A and B. Okay. Now if I draw, first of all, these are two solutions of your oblique shock. Okay. For this theta, like it was here, it was shown in theta beta curve, two solutions. So same way here, two solutions. Now if you draw one line from here joining B and if I draw a perpendicular here, okay, on this line, then the angle, so this angle, so I drew a line from C to D to B, and then I got a perpendicular OH on this line DH. Okay, so this angle that I'm getting here is your shock angle, beta. Okay. And if I join this here with point E, so this angle is your theta max, right? Beyond this, if theta is going to increase, then you're going to get a detached shock, right? So this is your shock polar. Then is your pressure deflection diagram. So it is something like this. P static pressure. Now this theta here is theta max, and this is some theta, random theta. Corresponding to that, we have this static pressure here. This lobe is for your left running oblique shock wave. This is for your right running oblique shock wave. Now, what is left running and what is right running? So if you're standing on the shock wave, okay, and uh, you're facing the flow direction, okay. So if your flow is moving in front direction, so you're also facing that direction. In that case, if your flow is deflecting in left direction, that we call left running wave. If your flow is moving in right direction, that is right running wave. By that logic or convention, this becomes a right running wave. Okay. And this becomes a, so this is left running, this is right running. So this is your pressure deflection diagram. Then is your regular reflection of oblique shock. After that is your wave reflection from a free boundary. So regular reflection, I can skip. And in your wave reflection from a free boundary, so what happens here is that your oblique shock. So at the exit of the a jet, you can see such free boundaries. Okay. So what happens is that your oblique shock gets reflected as a expansion wave, and your expansion wave gets reflected as oblique shock. So this is there in your, in short, in your wave reflection from a free boundary. Okay. Then is your week number 9. Isentropic supersonic nozzle flow, adiabatic nozzle flow, and then nozzle overexpanded, underexpanded. So so in case there is no shock in the nozzle, okay, so the flow is going to be isentropic supersonic nozzle flow, right? And in case we are encountering a shock within the nozzle, then we cannot say it's isentropic, right? So this is your week number 9. So we can understand it from this diagram. Okay, so this basically is a convergent divergent nozzle where we have here we have reservoir. Then this is entry of the nozzle. This is the throat. Then we have divergent section, and this is the exit. Okay. So initially we'll have some reservoir pressure. Okay. Now you can see in uh, till the point flow reaches at the throat, its pressure, static pressure is decreasing, right? That means it is accelerating and its static pressure is decreasing. Your flow velocity is increasing and its static pressure is decreasing, right? Then, then the flow in the next section depends on your back pressure, right? So, if your back pressure is not sufficiently low, okay, so your flow in your divergent section is going to be subsonic, okay, which is the case shown with this dotted line, okay. And as you keep on decreasing the back pressure, so what happens is that even in your divergent section, flow starts to be supersonic, right? So you decreased your back pressure and your flow is again supersonic till this point, right? But then what happens is that there comes a point where your exit pressure, right? Your exit pressure is lower than your back pressure, right? So if your exit pressure, so exit this, what I'm saying is exit pressure. Exit pressure corresponds to your flow, okay? The flow that is happening in your nozzle. So if this pressure is lower than your back pressure, it means that your flow has expanded to its maximum limit and there is no further scope that the flow can further expand. Okay, so this case we call as overexpanded case, right? That has been shown here in as number one, right? Then there is case where your back pressure is equal to your exit pressure. That is the design case, right? And in case your exit pressure is greater than your back pressure, right? That is your underexpanded case where you cannot further expand this, where you can further expand this flow. Okay, there is still scope that this flow can further be expanded. So that is basically there. Okay, this is your nozzle flow. Okay, then so this I have covered. The supersonic wind tunnel is there, and then related to that, supersonic diffuser is there. So supersonic wind tunnel. Your supersonic wind tunnel will have two throats. Okay. This is your reservoir section, nozzle test section. This is diffuser. So this is your throat 1. This is your throat 2. And your dia of throat 2 is greater than your dia of throat 1. Okay. In your supersonic wind tunnel. And why we use diffuser? So that we have minimum pressure losses in our wind tunnel. Okay. There is Rayleigh curve and Fano curve. Rayleigh curve is related to your heat and Fano curve is related to your friction. This is a Mollier diagram like this. So if your flow is subsonic and you heat it, it is try to move towards sonic state. And if you cool a subsonic flow, it is further going to, its Mach is further going to decrease. If you are going to heat subsonic, supersonic flow, it will also try to move towards sonic state. That is, its Mach is going to decrease. If you are going to cool a supersonic flow, its Mach is going to increase. Okay, it will try to move away from sonic state. Then Fano curve. And in your Rayleigh curve, so A point is your sonic state point. Okay, with maximum entropy. And B is for your maximum enthalpy. So your Fano curve is like this. Again, Mollier diagram. So it is like this. Upper section is for your subsonic flow and lower section is for supersonic. So with friction, this moves in this direction, this moves in this direction. Now in your Rayleigh curve, okay, so you can move from subsonic state to sonic state and sonic state to supersonic state because of heat, cooling and heating. But here that cannot be done. Okay. So let's say from supersonic state, you're moving to sonic state because of friction. Now, if you say that I want to move to further subsonic state from sonic state, that is not possible with friction. So this is your Fano curve. So number 10. Then experimental facilities for compressible flow measurement diagnostics. So in your compressible flow, we basically are tracking the density variations, and then temperature measurements are there and pressure measurements. So temperature measurements, one important this instrument we use is thermocouple. Okay, using thermocouple we do temperature measurements, and for your pressure measurements we have pitot tubes. Okay, there are simple pitot tubes also, and then there are pitot static tubes also. So pitot static tube will give both your total pressure and your static pressure, and your pitot tube will only give your total pressure or your stagnation pressure. And then measurement of flow velocity from your pitot static tube, you can get flow velocity for your subsonic flows. Okay, because you have dynamic pressure, you have total pressure, and then you have static pressure, and you have total pressure. From there, you can get the dynamic pressure. And in your supersonic flow, you have this relations. So you have pressure data and from your pitot tube, and then you have few relations using which you can get your pressure data. Okay, or MAC data you can get. Then there are Schlieren and shadow graph techniques. First is that the Schlieren technique is if you want to practically set up this Schlieren technique, this is expensive than your shadow graph technique. First is this. Then second is that both are optical instruments. Okay, both Schlieren and shadow graph. Then about if you see about your Schlieren, so Schlieren your first derivative of density. Okay, and this is your second derivative of density is used in your shadow graph technique, and in your Schlieren apparatus, first derivative of density is used. Okay, and in your shadow graph technique, so your variations in illumination of picture on the screen is proportional to your second derivative of density. Okay, basically what happens is that you have flow. Okay, flow happening, right? Now, because of density variations, your uh, light is going to refract. Okay, and this refraction we can use this refraction to design our apparatus like Schlieren and shadow graph. Okay, so that is the main idea behind these two optical instruments. Then is your wind tunnel instrumentation. So this is basically subsonic wind tunnel that has been discussed in your week number 11, where we have discussed from pitot static tubes to your hot wire anemometers. Okay. So because of resistance change in your hot wire anemometer, so we use a very thin wire. So we have in hot wire anemometer, we have a very thin wire that is connected to two prongs like this. So we'll have two prongs, and one this wire, very thin wire, this very thin tungsten wire is connected to these two prongs, and then this is connected to through some wire to some DAC. So there is, because of flow, there is heat transfer from this uh, wire, tungsten wire, which leads to the resistance change in this wire. And using King's law, we use this data and get our velocity. So so if you want to study turbulence, so this kind of instrument is of great use. So if you want to study boundary layers, so this instrument is of great use. So this is there. And the setup we have seen of your subsonic wind tunnel. So it is like this. So you have a settling chamber, then you have a contraction zone, you have a test section, you have a diffuser, and then you have a drive section. So at drive section, you're going to have a fan that is going to drive your wind tunnel or drive flow into the wind tunnel. Okay, settling chamber is to straighten the flow. Okay, and then contraction zone is to speed up the flow. And in test section, we keep our model on which we want to study its aerodynamics, okay, or hydrodynamics. In case it's a water wind tunnel, obviously hydrodynamics, right? Then we have diffuser to slow down the flow, okay. So this is your subsonic wind tunnel. Then week 12, supersonic wind tunnel we saw. So this I have discussed. So high enthalpy impulse test facilities and shock field. So in high enthalpy impulse test facilities, two facilities uh, that are important. One is your shock tunnel. So this is your shock tunnel. Then we have expansion tunnel. So your shock tunnel can generate hypersonic flows. Expansion tunnel can generate your hypervelocity flows. Okay, hypervelocity means of the order of 8 kilometers per second. Then there is shock tube also. So in shock tunnel, we have a driver section. So we have tubes. Okay, one is your driver section tube, then is your driven section tube, separated by an aluminum diaphragm. Then at the end of driven section of this shock tunnel, uh, you have a paper diaphragm, and this driven section is connected to a CD nozzle. Then this nozzle is connected to a test section. Okay. Then this test section further is connected to a dump tank. So we pressurize this driver section. Aluminum diaphragm bursts here, give a shock. This shock then bursts the paper diaphragm, giving another shock that propagates in CD nozzle and reaching your test section, giving you hypersonic flows. Then your expansion tunnel, where you have a reservoir tube. Then there is a piston and a compression tube. Okay, compression tube and low pressure driven tube. So this compression tube is like your driver tube. Okay, and then it is separated from your driven tube by means of a primary diaphragm. Then this driven tube is connected to acceleration tube, which is at very low temperatures and separated from your driven tube by a secondary diaphragm. And this acceleration tube is connected to a divergent nozzle, and from there it is connected to a test section. So you, by means of increasing pressure in your reservoir tube, you move the piston. This piston pressurizes whatever gas is there in your compression tube, okay, which bursts the primary diaphragm, giving rise to a wave which further ruptures secondary diaphragm, and then you have a wave traveling from acceleration tube towards your nozzle. From nozzle, it reaches your test section. So this is your hypervelocity flow. It will generate a hypervelocity flow at the test section. Now in shock tube, what happens is that you have only a driver section and a driven section, and they both are separated by a diaphragm. So this basically is used to study supersonic flows, a shock tube. So we pressurize the driver section and the diaphragm bursts, giving rise to shock wave. Okay, and then this shock wave, we can mount at the end of the driven section, we can mount our models, and with appropriate instrumentation, we can study the uh, impact of shock wave on this models. Okay, so this is it about your course fundamentals of compressible flow. So we moved from, so now I'll conclude this session and this course. So initially we were introduced to thermodynamics and basic fluid mechanics. Then we moved on to 1D flows, 1D compressible flows we studied. From there, we moved on to quasi 1D flows where we studied area Mach number relation, right? Area Mach number velocity relation we saw there. Then we from there we moved on to normal shock waves. So we studied how we can model shock waves using a piston, and then how the flow properties change across normal shocks that we studied. Then from there we moved on to oblique shocks and expansion waves. So if your flow is being moved towards itself, then we get a oblique shock. And if it is moving away from itself, then we are getting expansion waves. Then we saw how expansion waves can be modeled. Okay, by using a piston, how we can model expansion wave. This we saw. Then from there we moved on to uh, how your compression waves. So we studied nozzles and diffusers. So isentropic nozzle and adiabatic nozzle flow we saw. So different cases like subsonic flow, underexpanded flow, overexpanded flow, design condition. What is design condition that we saw? So from there we saw how the supersonic flow behaves with heating and cooling, and then how it behaves with friction. From there, we saw the experimental part of compressible flow. So how we can perform experiments and try to study compressible flow. So different types of setups we saw. Okay, which can study flows ranging from supersonic to hypersonic, hypervelocity flows. So this is it about this course. I hope this course has been a learning experience for you all. Okay, and I wish you luck for your final exams. Thank you. Thanks for watching this session.